Good evening. Welcome to another edition of DEBAKEY CV Live, Innovation on the Loose, streaming live from Houston Methodist Hospital here in the Texas Medical Center. I'm Dr. Stuart Corr, Director of Innovation Engineering for the DEBAKEY Heart and Vascular Center. Tonight we will be taking another trip into extended reality to learn more about wearable haptics and XR worlds. To that end, I'm delighted to have Professor Marcia O'Malley on the show. Professor O'Malley is the Associate Dean for Research and Innovation at the George R. Brown School of Engineering at Rice University. She also leads the Mechatronics and Haptic Interface Lab, and we will learn more about her research program and developments in tonight's show. Before we proceed, I would like to invite the audience into our discussions. Please submit your questions via web at polyev.com using DEBAKEY as the username, or text DEBAKEY to 37607 alongside your question. You can also add your question into the live YouTube stream. Now, for those of you who can remember, we officially launched a new initiative back in September 2021 called the Houston Methodist Institute for Robotics, Imaging and Navigation. The launch was in the form of the first ever symposium, as you'll see on these slides here. The first ever annual symposium. Where are we here? Okay. There we go, guys. The launch was in the first, it's one of those days. The launch was in the form of the first ever annual symposium for the Institute with the theme of exploring extended reality and robotics. At this virtual event, hosted on YouTube and Hopin, we were delighted to have a full host of participants from a variety of industrial and academic collaborators. Now, keeping up the momentum, we then went on to form the official YouTube channel and content provider for the Institute, which we are calling Robotic Health. Now, our Robotic Health channel is a place to go to learn about all of the Houston Methodist activities in the areas of robotics, imaging and navigation, including our newly established Center for Extended Reality. Now, you can go there by typing robotichealth.org. I would also like to bring to your attention the Houston Tech Rodeo Roadshow, which will be happening all of next week, February 27th to March 5th. A week-long corralling of the Houston Tech community, spurring new connections, ideas, and innovation. The Houston Tech Rodeo is a festival that celebrates the convergence of popular culture and innovation in Houston. Founded in 2020, the Houston Tech Rodeo has quickly transformed into an essential destination for founders, future and present, and talented individuals to spur new connections and ideas while highlighting all that Houston has to offer. This year, concentrated along the Metro Red Line, the 2022 Houston Tech Rodeo Roadshow provides unrivaled access to the Houston startup ecosystem. So saddle up for 5 days of community-driven content designed to connect, develop, and showcase Houston innovation. And this year, in collaboration with Houston Methodist and the Texas A&M EnMed program, the MedTech Saloon will take place at the newly built EnMed building located at 1020 Holcomb Boulevard. Now, here is a quick snapshot of that MedTech agenda. We have a fully packed theatre event that brings together some of the local leaders and stakeholders in health tech and digital health. And more excitingly, because I think we're the ones that are putting this bit on, in addition, for those of you that are interested in getting hands-on experience with extended reality systems, we will be running a theatre XR workshop with the partners Mace Virtual Labs and Fundamental Surgery. You can register at htcxtechrodeo.com. Now, I'd actually be delighted to turn this part of the show over to my special guest, Professor Marcia O'Malley. Dr. O'Malley, welcome to the show. So, if you could, I'd love if you could just give the audience a little bit, an overview of where you are, what you're doing at Rice, and then we can lead into the presentation.
Absolutely. So I'm trained as a mechanical engineer, and I've been on the faculty here at Rice for just over 20 years. My research is focused on how humans and robots can physically interact. So I'm interested in how we can use robotic devices in physical contact with humans to enhance their performance. In some applications, we're looking at training and learning new skills, and I'll talk a little bit about our work relative to a collaboration with Methodist in the talk this evening. In other cases, we're looking at restoring function that might have been lost after neurological injury, like stroke or spinal cord injury. And in other scenarios, we're just having fun with providing touch feedback from virtual or remote environments and thinking about how we can use actuated devices that are worn to give the sense of touch to those interactions.
Okay, well, I think we need to go ahead with the presentation. I'm very excited. You know, I've been trying to get you on the show for a while, and I'm really glad we carved out a little bit of time with schedule. So please carry on with the presentation, if you may.
Will do. Let's hope that the technology is with me. Let me make sure okay. Is that looking good for you right now?
Perfect.
All right, so yeah, I'm really excited for the opportunity to join the show and talk about what we've been doing in my lab at Rice in wearable haptics for XR environments. And let me just start with an introduction to haptics. So haptic, you know, when I first started doing research in haptics 25 years ago, I had to define it for everybody. Maybe I don't have to do that anymore. But haptic refers to the sense of touch. And one of the things that's really interesting about touch compared to our other senses is that it's bidirectional. So, you know, my sense of vision, I can look at an object, I can look at the screen, but I can't change what I'm seeing. With audition, I can hear sounds around me, but I can't directly affect that sound through my own sense of hearing. But with touch, it's bidirectional. I'm interacting with objects. I can feel how they change in shape and form. And touch is distributed all over our bodies. So it's just the, you know, it's the largest sensory organ, our skin. And so there's just lots of interesting opportunities for how we can think about providing touch feedback to individuals. And another thing that I think is interesting about touch is there's different ways to experience touch. So we talk about active touch versus passive touch. So active touch would be what you see here, individuals moving their hands over these texturized displays and feeling the response of the objects that they're touching. But we also can experience passive touch where, you know, I can reach out and put my hand on your shoulder and you can feel that without any action of your own. And so that would be you as a passive individual experiencing touch cues that are applied to your body. So to set the stage for the research that we've been doing, I'll do a little bit, a very brief history of haptic technologies. So when I started in the field of haptics, it was the late 90s, and the focus was on the design of what we call grounded haptic devices. And what we were interested in doing was rendering kinesthetic type haptic feedback. So what I mean by kinesthetic is that these are the forces and torques that are experienced as you explore the world, touching objects, feeling weight or stiffness or compliance. And so a lot of these early devices relied on a stylus, a tool that was the interaction point between you and that virtual world that you were feeling. So it's basically like exploring the whole world through dental tools. So a decade or so later, with the advent of tablets and smartphones, haptic research really shifted and started to focus on what we call surface haptics, or how to convey textures and tactile sensations through the fingertip, exploring a surface. This is done either by vibrating the surface of the screen to modulate the friction between the fingertip and the surface, or using technology like electrostatics. And while there's challenges for how you create multi-touch scenarios, a ton of progress has been made here in surface haptics in recent years. But what I find really exciting about the field of haptics is just the explosion of wearable devices. And more of wearable devices are providing haptic feedback. I'm sure that while I'm sitting here talking with you tonight, my smartwatch is going to give me some vibration notification that I've got a text or a phone call. And you know, maybe it's even going to tell me I need to stand up and walk around. My group, along with other groups around the world, is really interested in how we can enhance the range and type of haptic feedback that can be provided with wearable devices so that we can move beyond simple notifications like I just described and really use this mechanism to help people navigate, communicate, and convey really information-rich messages. So while haptic devices started off as grounded devices made of rigid links, they depend on accurate sensing of the stylus, position, and orientation. We've really shifted away from that to getting devices off of desktops, detached from walls, and onto our bodies. And in fact, a lot of wearable haptic devices for interactions in virtual reality have taken the form of gloves that apply forces directly to the fingertips, like these gloves that you can see here from Haptics. Now, in virtual reality scenarios, we aren't necessarily trying to move the limbs around, right? Our gamers are they're used to donning a headset and interacting in VR. What we really want to achieve is a believable haptic feedback effect that the user associates with the effort of interacting with virtual objects. And if we can do that without bulky hardware on our hands, even better, because then that opens up the opportunity for XR environments where we might be interacting with a mix of virtual and physical objects in the environment that we want to be able to touch with our hands when they're physical and real, and we also want to experience when they're virtual. So in my lab, we've been working on a collaboration with the company formerly known as Facebook, with their research division called Facebook Reality Labs, now Meta, to develop wearable haptic devices that can convey realistic haptic or touch feedback to a user interacting with objects in either virtual or augmented reality. So as you saw in the previous slide, commercial haptic devices tend to be either really expensive gloves that are bulky but offer really extremely believable interactions, or they tend to be these sort of handheld controllers that maybe you or teenagers in your house are used to holding, that have just very limited haptic feedback. But there's sort of trade-offs to all of these, right? So there's cost trade-offs and the amount of encumbrance on the user, there's power requirement trade-offs, and there's fidelity trade-offs as well. So we sought to develop a device somewhere in the middle of this spectrum, and went with the bracelet design that has the advantage of leaving the hands free and being all-day wearable and socially acceptable in public. So I want to talk to you a little bit about the kinds of sensations that we're trying to target with touch feedback, with this haptic feedback device. So a little bit of the physiology of touch. Wearable haptic devices can contain different kinds of actuators intended to elicit responses from the mechanoreceptors in our skin. So I said touch is much more nuanced than vision or audition, and that's because we have different sensors in our skin that respond to different kinds of stimulation. They respond to different ranges of vibration cues. They respond to temperature. Some are more attuned to pressure or textures than vibration itself. So when we want to convey haptic feedback to a user, it's really important to consider both the mechanism of actuation, so how we're actually going to push, pull, or squeeze on their limbs, but also the capabilities of their sensing. Another thing to consider is that mechanoreceptors are really sparse on our arms compared to our fingertips. And so we have to take that into account as well. So our choice to come up with a bracelet interface means that we have sort of limited sensing resolution. I know some folks take their smartwatches and program in different notifications for texts from different people. And I can tell you honestly, I don't have the sensory precision to be able to tell the difference between those notifications and cues. It's just because I have limited sensors on my wrist. But we want to think about how we can really take advantage of this real estate where we're used to putting devices like our smartwatches and really add that haptic experience to our users. So we created this device called Tasbi, a tactile and squeeze bracelet interface. And as its name implies, Tasbi can deliver vibrotactile feedback to 6 different discrete locations around the wrist. So this gives us an advantage over existing vibrational controllers in that we can program richer and higher throughput cues to the user. But what's really exciting about Tasbi, and what I think is its most interesting feature, is its ability to apply pressure or squeeze to the wrist. So this second haptic modality allows us to provide proportional feedback for interactions where vibrations are not well suited. And I'll tease you with some videos in a little bit. So this is a video with an example of the squeeze action of Tasbi. So here you're seeing the squeeze actuator being commanded to follow a sinusoidal motion. It's the same, here's the same motion showing it on the arm. And one thing I want you to notice is how the squeeze actuation pushes each band element directly into the skin instead of pulling across it. A lot of devices that have been developed for squeeze are more like a strap that tightens, and you feel not just the squeezing force, but you feel that strap sliding against the skin. And here we really isolate the squeeze. And then under each of those rectangular tabs is a vibration motor that we can command to work in concert with the squeezing effect. So now I'm going to let my former PhD student, Evan Pezent, in a video tell you about all of the exciting things that he has created with Tasbi.
Our approach to creating believable interactions has 3 parts. First, haptic vibrations render discrete events such as hand collisions, impacts, and high-frequency content. Second, we use proportional squeeze for continuous forces such as object stiffness, weight, and inertia. Finally, visual pseudo-haptic effects manipulate the virtual hand position to give the illusion that certain actions require more physical effort. Let's take a look at some examples. In this button interaction, vibration is rendered when the user contacts the button's surface and fully depresses it. Squeeze increases as the button is pressed to convey a spring stiffness. In fact, by increasing the rate of squeeze and the intensity of the pseudo-haptic effect together, it is possible to make buttons that feel harder to press. Vibration, squeeze, and visual pseudo-haptics can be applied to other motions such as pulling and twisting.
So that video shows some of what we call the interaction primitives that we've been able to realize with Tasbi. And now let me show you, we've got a number of different demos that we offer in the lab, but I'll show you one that I think is the most exciting. And that is when you put a Tasbi on each wrist and then you get to do some bimanual tasks.
Tasbi is most compelling when haptic feedback is provided on both hands. This is especially true for two-handed interactions that simulate reactive forces between the hands, such as this bow and arrow example.
So as you can see, when we combine these haptic cues with the pseudo-haptic visual illusions in virtual reality, we are able to create believable substitutions for interactions that otherwise occur at the hands and fingertips. And this work really highlights an opportunity for overcoming the typical low-fidelity cues of wearable haptic devices by leveraging the manipulability of the visual display to allow us to improve realism, immersion, and the salience of the haptic effects in virtual and augmented reality. When you combine this approach of manipulating the visual feedback with actuation choices that overcome the user's perceptual limitations and avoid perceptual interference and masking of cues, you really have this playground in which to design these haptic experiences as you design your virtual environments. So I want to shift gears now and talk about a particular application of wearable haptics that we're pursuing in collaboration with Houston Methodist. So we've been collaborating with Houston Methodist on aspects of training in endovascular surgery. So for the non-medical folks in the room, endovascular surgery is a minimally invasive approach that enables doctors to treat vascular conditions while minimizing trauma. It's accomplished by navigating a catheter introduced in the femoral artery to a treatment area. And these catheters, guide wires, and sheaths have different physical properties, and they must be manipulated in tandem to navigate the complicated vasculature. I've tried this myself, don't worry, only in simulation, and it's really difficult to do these navigation tasks. It's also a difficult procedure to learn. And one of the reasons for that is that trainees are limited in the amount and quality of feedback that they receive, limited in time because expert surgeons are quite busy and their time is valuable. And second, limited in sort of the quality or detail in the feedback that they receive. So here, even in this video, you can see the trainee inserting the flexible guide wire and catheter into this model of the vasculature. And the individual behind them with the piece of paper is the observer who is watching them and grading their performance using checklists. So the work that I'm going to describe has been a really fun multi-year collaborative effort with Dr. John Bismuth and his team and my colleague Mike Byrne at Rice and a number of students and postdocs in both of our labs. And we're really grateful for the financial and in-kind support provided by NSF and our industry partners. And just the access to the expertise that we've had at Methodist has been fantastic for this project. So becoming proficient in using these flexible endovascular tools like guide wires and catheters can be really challenging, as I mentioned. And a major reason for this is the non-intuitive mapping between the movements made by the surgeon at the entry port and the resulting tooltip motions, which depend both on the surgeon's actions and interactions between the tools themselves and the vasculature. So here you can see that non-intuitive mapping. So the actions of the individual are controlling the relative position of the guide wire and catheter. And at the end, you're getting this motion of this pre-curved guide wire in the anatomy. It's also really difficult to visualize the anatomy, which depends on radiographic contrast and fluoroscopy or real-time X-ray. So you can see here you have at times really good visualization of the vascular structures, but you have to keep injecting additional contrast and updating the fluoro to get those images. And finally, the last piece that makes this really challenging is that the 3D vasculature is displayed as 2D cross sections. So here on the right is the view that the surgeon gets when they're inserting the catheter into the vasculature, but obviously we know that branching structure is three-dimensional, and that makes it challenging to learn how to do these navigation tasks. So one thing we do know is that this is a procedure that benefits from training and practice. Many studies suggest evidence of learning curves resulting in decreases in procedure time and decreased use of fluoroscopy, which has advantages in reducing radiation exposure and contrast dosing. We also see increases in postoperative success rates and decreases in complications and postoperative mortality rates with training and practice. And what's really interesting is the sharp change in performance that's often noted after about 50 or more consecutive cases. So really, it's an application where more practice is beneficial, and we really are interested in maximizing training efficiency and efficacy to either achieve these results more quickly or to improve overall performance gains. So one challenge that we have in the field is the type of performance feedback that trainees get. So currently, the methods of assessing performance are relatively subjective and qualitative in nature. You saw in the video the individual with the checklist standing over the trainee's shoulder. So that he was using a structured rating scale. As a senior level examiner would have the expertise to make that assessment. And these grading scales require that expert to oversee the process and do the evaluation. A drawback of this is that trainees don't receive feedback on how to change their strategies or improve their performance. They just get a grade. So here they might get scores of 1s and 2s, and that's determined to be a fail. And maybe they're kind of at an intermediate level and it's good enough to pass, but what we really want is our trainees and surgeons to be excellent at these tasks. So this led us to ask, can we automate assessment using objective and quantitative metrics? And if so, could we then use these assessments to evaluate new technologies? But what I'm going to focus on today is, can we provide objective feedback during training to help trainees improve their skills, to basically give them the coaching they need to know how to change their strategy to improve their overall performance and outcomes. So we really are motivated to do motion-based assessment. And what I mean by that is taking advantage of advanced technology that gives us information about the movements of the surgical tools themselves and allows us to analyze those tool movements and infer performance in an objective and quantitative way. Now, these methods, these motion-based assessment methods, have been used extensively in laparoscopic procedures, but less so for endovascular surgery. So we saw a real opportunity here. So now you're going to get a quick lesson in human motor control. And this is the question, what aspects of motion should we analyze? So I show you here two figures. So the figure on the left is showing like a start point with the plus sign and a target with the circle. And we ask an individual to make a straight line movement. And a skilled person, even if I ask you to, make a straight line movement to reach out and grab your glass of water, your path will be quite straight. And so we can measure deviations from that path as a way to infer your skill. But what's really interesting is to look at not just the path itself, but the speed along that path. So the plot on the right is showing speed versus time. And if you are reaching out to your water bottle to get a drink of water and you follow that straight line trajectory, what you also will exhibit is this bell-shaped velocity profile where you start at zero velocity and you end at zero velocity and you hit peak velocity in the center. And a bell-shaped velocity profile or speed profile like this is called a minimum jerk speed profile. And this characteristic of this bell-shaped profile is called movement smoothness. And movement smoothness is widely regarded as a hallmark of skilled and coordinated movement. And smoothness-based assessment has been validated in a number of other domains, including rehabilitation contexts and manipulation of flexible objects. So there's lots of different ways that we can assess smoothness. One way is to look at how your own speed profile, that red jaggedy curve, correlates to that optimally smooth or minimum jerk speed profile. Another way that we can analyze smoothness is to think about the frequency domain. And that would mean that if your movements are really, really jerky, you'd have, or less smooth, you'd have lots of oscillations if you look at the frequency domain. And if your movements are more smooth, they're comprised of one or two primary frequencies, then you would have the top row, that more smooth speed profile and frequency spectrum. So that's maybe more engineering than I probably needed to get into at 5:30 on a weekday. But the idea here is that we can look at characteristics of the movement that the surgeons and trainees are making, particularly the movements of the tools that they're controlling. And from that, we can infer their expertise, their coordination, and likelihood of success. So we set out with this goal in mind and wanted to answer the question, do motion-based metrics correlate to skill in endovascular procedures? And with the fantastic resources that we have available to us in collaboration at Methodist, we were able to do this in 3 different platforms. So what you see across the top is what I call the manual catheterization of a physical model. So we have an anatomically inspired model of the vasculature, and we can put this under a C-arm and look at live fluoro as individuals navigate and insert that guide wire and catheter into the model. We can also do this in virtual reality. And so in collaboration with what was Symbiotics and 3D Systems and is now the company Surgical Science, we have access to this endovascular simulator where we can load a CAD model of that exact same vascular model and have trainees insert the guide wire and catheter into the simulator and practice navigation. And then we also have robotic platforms at our disposal. And so we can look at how these trainees navigate guide wire and catheters that are robotically actuated to access the vasculature. In each of these cases, we have technology and sensing that enables us to track the tooltip motions of those guide wire tips. So we record those versus time. We derive the measures of smoothness from that data. And then we look at correlations or comparisons depending on the expertise level of our participants. So I'll just show some fun images of what this looks like. So here is an individual inserting the guide wire and catheter into the simulator, and you can see the resultant motion of the guide wire tip up here. That's that top dot, the catheter tip, and this is the sheath tip. And so they're trying to get all of those points lined up to targets. And throughout the process of this navigation, we're recording data and computing how smooth the movements of those tooltips are, and then correlating those to their expertise, either based on caseload or based on that structured grading checklist assessment that we had an external expert determine. So the takeaway of, I always hate to condense the work of multiple PhDs into one slide, but the takeaway from that initial question of does Can we assess surgical skill using these measures of tool movement smoothness and correlate them to expertise was a resounding yes. So just summarizing our process, we track the tooltip movements and extract the velocity profile of the tooltips. We convert that into the frequency domain and compute a measure we call spark. That tells us the degree of smoothness of the movement. And then we look at correlations between that smoothness measure here on the y-axis and the score in that structured grading assessment. And what you see is this nice, strong correlation between their measure with that movement smoothness metric and their performance on the structured grading scale. And just for fun, we colored the expertise level of our participants based on their prior caseload. So novices had less than 50 cases. Experts had more than 500 cases. They're in red, and then the intermediates were in between. And you can see, as expected, it sort of lays out along that line. And so we can also group our participants and look at average scores for novices, intermediates, and experts, and really saw this very strong correlation between expertise and performance with the smoothness-based metrics. So now that we know we can objectively assess performance, that was really an exciting finding. But the way this happened was we would collect all that data and then go back to the lab, crunch all the numbers, and weeks or months later say, aha, there's a correlation. What we really want to be able to do is provide that feedback in real time. So we ask the question now, does the provision of feedback affect performance? So now the idea is not just collect all the data, go home, process it, and come back a few months later with the answer, but can we compute these measures in real time while the participants are navigating these vascular structures and give them cues, while they're performing in how they might change their behavior. So one thing we learned in our collaboration with Methodist is that surgeon time is very valuable and hard to schedule. And so what we wanted to do was come up with a proxy task that we could use in the lab. So we're going to step away from the surgical domain so that I can explain our most recent work, and then I'll circle back on how we're going to bring this back to the surgical domain. So the challenges that we have in this case are, how do we assess performance in real time? It's not trivial to go from post-processing data to computing these measures as the tasks are being done. How do we provide that measure? How do we encode smoothness as a feedback? And then, how are we going to sort this out and figure out how to do this? And will this approach actually affect task performance strategies? So in order to develop and test our method of feedback, we first had to design and validate a suitable proxy task for endovascular surgery. So the task we chose is based on a mirror tracing task originally introduced back in the 1920s. In this task, the controls are inverted along both axes to increase difficulty. So our subjects used a 3D joystick called the Novant Falcon with motion restricted to 2 axes to navigate and trace this complex shape. To move the cursor, you had to go in the opposite direction. So to move the cursor up, you actually had to move the joystick down. To move the cursor left, you had to move the joystick to the right. And subjects were tasked with completing a trace of this shape as quickly and accurately as possible, trying to stay in the lines. So the basic structure is this. We have the joystick that's acquiring data about the position of the user. So that's our real-time data. We export that and compute our metrics of smoothness. And then we encode that into a tactile cue that we provide to the user's arm. And they're getting this feedback all the while that they're tracing this, this shape, be it a star or the curly shape that I showed you on the previous slide. So we wanted to encode the performance feedback, but we were interested in testing a few different ways of encoding that information. So we compared a few. So if you think about tracing the shape, so imagine these 2 black lines across the top are the channel that we want you to move through. You can imagine the cursor location going in and out of that channel as you deviate from the path. So we had one group of participants who received position feedback. If you've ever played that operation game where you get buzzed if you hit the sides as you're trying to pull the funny bone out of the elbow, it's exactly like that. So if you go out of bounds, then you feel haptic feedback, this vibration cue telling you went out of bounds. And then we had a more complicated paradigm for smoothness feedback. So here we're looking at the velocity profile, not the position. And when that velocity profile is really non-smooth, then after 5 seconds of non-smooth behavior, you get buzz telling you you're 3 times. That was not very good. As you improve your performance, you get a moderately smooth feedback of a couple of buzzes. And when you are able to navigate that cursor in a very smooth manner, then you get this nice, comforting, soft single buzz. So every 5 seconds, this group getting smoothness feedback would get 1, 2, or 3 buzzes corresponding to the quality with which they were able to move that cursor for the previous 5 seconds. And then we had one more group that was a no feedback condition. They were just our control group that basically just practiced the task repeatedly without any real-time feedback. So I'll jump right to the results. And these are the kinds of plots I like to see. So the red group is our smoothness feedback group. And what we noticed with them is that their total task completion time was faster than the other 2 groups, faster than the control group in blue that just practiced, and faster than what I'll call the operation feedback that got buzzed when they went out of bounds. All of our groups rapidly improved between the first and second trials, but we saw this just sustained better performance by our smoothness feedback group. So this is looking at their task completion time, the time it took them to trace the shape. We can look at other measures as well. We can see here, looking at their smoothness, that the group getting feedback about how smooth their movements were able to execute more smooth movements. And we can also dig into the data a little bit more. We were able to see trade-offs that we experience. So here on the left, we look at the amount of time the individual stays inside the trace and the time they spent outside the trace. And what we notice is that all the groups get faster at the task. The gains of the smoothness feedback group are greater than the other 2 groups. And we see that smoothness group spends more time outside of the figure than the other 2 groups, but it's really just on the order of a couple of seconds for the course of the task. So they sacrifice a little bit of improvement in accuracy, but not much for big gains in task completion time. So this was our lab study. We were able to, use lots of Rice undergraduates as our participants, but we really validated this approach, this idea that we can give feedback based on movement smoothness and see how we can manipulate or influence, maybe influence is a better word, how we can influence the strategy that these participants use to complete the task by emphasizing the quality of the movement and not the outcome of trace the shape quickly. So let's get back to the surgical domain. Now that we have validated this approach to providing feedback based on movement smoothness with our proxy task of mirror tracing, the next step is to take this back to the surgical context and explore methods of real-time performance feedback that might elicit improved accuracy while maintaining the reductions in completion time that were achieved with smoothness-based feedback for that mirror tracing task. So we, again, have access to this physical model, and we can put the physical model under a C-arm, and we can look at how folks navigate. But now we can also use that endovascular simulator. And one of the advances that we have now is we're working in close collaboration with surgical science. And so they're actually providing us real-time data about catheter and guide wire tip locations. And we're able to stream that in real time and compute these measures of smoothness. And our goal is to provide that same haptic feedback right to the arm of our trainees and see if we can influence endovascular navigation performance in the same way that we saw for our mirror tracing task. So I kind of just summarize the second part, that we can use movement smoothness to correlate to endovascular skill. And these measures are effective at evaluating technology and mapping this really kind of abstract measure of performance, the smoothness feedback, to a vibrotactile cue was really successful at influencing the task completion strategies of our users. And so we're excited about launching this method of training onto the surgical simulators. We're in the process of rolling that out right now and hope to be collecting data on that this summer. What's exciting in particular is a partnership with 12 different residency programs around the nation, where we'll have a large pool of participants, some receiving that real-time feedback and some just practicing the task so that we can see the effects of this intervention that we're providing. So today I kind of gave you two different views about wearable haptics in XR environments. One being a little bit more, future looking, and how we can provide haptic feedback to the wrist through squeeze forces and vibration to really make you think that you're interacting with objects in your hand that have weight and mass, buttons that are compliant that you can press and interact with. It's really believable sensation. You'll have to believe me when I say it, because it's really hard to talk about haptics. But then I also brought our work in the surgical domain here to share with you our vision for how we can use this technology of wearable haptics to influence surgical training and hopefully benefit surgical outcomes and efficiency of training and residency programs around the world. So with that, I'll stop, and I'm really looking forward to some time to discuss with all of you.
Okay, thank you. Professor Mal, that was a very exciting and insightful overview of your research there. Yeah, I've got a lot of questions, so I'm going to jump straight in here. So now going back to the very beginning, with your haptic interfaces and the way that haptics are actually done now, it seems there's two mechanisms. One is kind of replicating the touch on your fingertips or your wrist, but it would seem that the other would be, for want of a better word, hacking and hijacking your neuronal pathway. Okay, so do you know of anyone that's kind of doing work in that area? Like is that a limitation? Maybe comment on that.
Yeah, that's a great question. So where we see the most advances in I like it, hacking into the neuronal system is really in the field of prosthetics. They've made a lot of advances of doing direct stimulation of neurons to elicit. I would say it's not. It doesn't feel like you're touching things, but there is a sensation associated with an action, and I think that's really what is the key to these haptic experiences. So with a stylus-based device that I showed, I can create very complex 3D objects that you can probe, and they're going to feel very realistic, but you're constrained to touching them through a single point. With the but at least the action-reaction is coupled. With the wearable device I showed on the wrist, even though it's not something pushing on my fingertip, I am feeling a squeeze and a vibration cue synchronized with the action of pushing this virtual button. And so it's not the exact touch sensation that I want people to have, but it's related enough that I'm able to integrate that information in my brain. And similarly with the work in prosthetics, the stimulation of nerves gets the nerves to fire and causes a response in the brain that can be trained to be associated with the experiences that the amputee is having using their prosthetic limb to grab everyday objects. So that's probably more invasive than your everyday gamer or maybe medical resident wants to subject themselves to. Most of the direct nerve stimulation is done invasively with electrodes that are inserted through the skin or cuff electrodes that go around nerve bundles. So it is an invasive approach, and but viable for those populations that can benefit from having that feedback.
So maybe down the road when we're looking at embedding smart technologies into our bodies, maybe that's the time that we can start looking back on using it for like VR and XR, etc. Now going to the endovascular applications, you talk about measuring the jerkiness, and you talked, you had this tool tip technology. Can you comment a little bit more about how that works?
Sure. So when we started out thinking about how we would assess surgical skill, we started with the hands. We thought, the surgeon's tools are their hands that they're using to interact and manipulate these flexible guide wires and catheters. And it turns out that tracking hand motions, especially in a surgical environment, is very challenging. You have lots of other objects, you've got occlusion, the hands are working in concert, very fine motions that are hard to detect. And so basically because of technical limitations, we had to pivot. And I was familiar with some literature on reaching movements and how we control to follow straight line trajectories and have these smooth movements. And I was familiar with some work where researchers had looked at how we manipulate flexible objects. So imagine that I'm, cracking a whip or even balancing you can put a pole on your palm and balance it back and forth. We are actually really good at transferring a plan from how I want to move my hand to how I want this object that I'm controlling to move. And so based on that literature that said humans are actually good at figuring out how to move their hands in ways that get the object to move, we thought, well, we can't track hands, so let's track tools. And it was really because of some new technologies in electromagnetic sensing that we could put very small sensors on the tips of the guide wires and catheters that were being used to navigate the physical models, both manually and with the robot, and just using image processing software to track those tooltip locations in the virtual environment. We had access to that and kind of took the risk to see if our hypothesis would hold. And it worked out better than expected to be able to show those correlations between those tooltip movements and expertise.
It's fantastic. And I saw in the experiments that they do involve the use of a haptic kind of control system, like where you're actually pushing down on the stylus pen or that haptic controller. I'm wondering, is there any, with the advancements in hand tracking technology, for example, in Oculus Quest, could you kind of replicate that whole experience without the use of the haptic controller?
Yeah, absolutely. So I think you really see that in the videos from the first half of the presentation. So when we started the work with Tasbi, the device on the wrist, we were using those handheld controllers that had the tracking embedded in them. And so we were relying on the handheld controllers to tell us where our hands were so that we knew how the individual was interacting with the virtual objects so that we could give them the right kind of haptic response. But now with the Quest and with other VR technology, the freehand tracking is really quite good. And that's where we have fun with those visual illusions. So that simple action of pressing that virtual button, there's three things happening. So the first is, as soon as you contact the virtual button, you feel the vibration cue. And that's just like the high frequency content you would get anytime you tap on an object. There's a little sort of spike of a cue. So we give the vibration when you come in contact with the virtual button. The second is the continuous cue, where you depress that button and you're feeling the squeeze force around your wrist. And the third piece that's really magical in VR is that I can detach where I represent your hand from where your hand actually is. So you can imagine a button that I only have to move my hand maybe an inch to depress, compared to a button that I have to move my hand 4 or 5 inches to depress. In the VR environment, all I see is my virtual hand moving this button 1 inch. But what I perceive when I have to move my hand 4 or 5 inches is that it takes much more effort. And so even though I'm not constraining the fingertip, I'm only squeezing here and playing with the visual feedback, I give you the illusion that it takes more effort to depress that button, and you feel like you've expended more effort, and thereby you think the button is stiffer. So even though it's all just in midair, it's magic.
That is magic. I mean, this whole field, I think, is magic. I'm just curious, the Tasbi, any thoughts on making that like an open source kind of project for people to play around in and whatnot?
Yeah, that's a great question. So I actually have a graduate student right now, Mike Fantini, who's working on a lower cost version of Tasbi. So we made Tasbi when we were playing with Facebook budgets. And so the mechanism, the custom motor and the mechanism to cause that squeezing are really high end, top of the line. There's embedded sensing to do closed loop control, an engineer's dream. But it's not practical, right? The hardware for just creating one of those is about $3,000 to $5,000. So we want to make it more accessible. And so he's working on some versions that use just off-the-shelf technology, little ERM motors that are the same things that make your phones vibrate when you have a notification, using just simple servo motors that you can pick up at any hobby shop. And so as he wraps up his research, we're going to be making those designs available for hobbyists or anybody who wants to fabricate their own. We use a lot of 3D printing now for our devices, and we are a lab that likes to share and make things open source. Certainly, let me know when you're ready for one, and we can make one available to you, Stuart. You can enhance your own VR experiences.
Well, I think the answer to that is we're ready now. So as soon as you have one ready, please send it over.
I'll let Mike know that he needs to speed up his graduation timeline.
Awesome, love it. Well, I think that's all the questions from myself here. Do you have any further comments you'd like to say to the audience?
I'll just say, I have been really fortunate to land in Houston as a faculty member and really just, reap the benefits of the collaborations across the street. And what's been so fun about this surgical training project is that we're really, all of the collaborating team is really pushing forward and is all invested in how we can enhance training. We each have our own piece to it. So there's certainly the folks who have like the educational and residency training and accreditation piece. For me, it's, can this technology really influence learning and training? And I'm really excited what you guys are doing with the XR initiative and with Mirren, and looking forward to more years of fruitful collaboration.
That's great. Well, I think on that note, I think that will be an excellent note just to say we're adjourned, I guess. So, Professor O'Malley, again, I'd like to thank you very much for appearing on the show. This has been absolutely fascinating, an eye-opener here. To members of the audience, this show will actually be available on demand in both the DEBAKEY CV Education YouTube channel, but also our Robotic Health YouTube channel. As part of the Robotic Health YouTube channel, we have the Center for Extended Reality. We have a big playlist there, so this fits in really nicely to that. So again, Professor O'Malley, thank you. Good evening. Goodbye, everyone.
Thanks, Dr. Corr.